Today in DC electrical circuits, we're going to take a look at lab number 10, Superposition Theorem. The objective of this exercise is to investigate the applications of the superposition theorem to multiple DC source circuits in terms of both voltage and current measurements. Power calculations will also be examined. Under the reference sections, I'm referring to Sherman's Outline, Basic Electricity, 2nd edition. And we're going to take a look at chapter number 9, Network Calculations, specifically Superposition. So in Sherman's Outlines, chapter 9 is about network calculations. And under superposition, it says the superposition theorem states that in a network with two or more sources, the current or voltage for any component is the algebraic sum of the effects produced by each source acting independently. And example 9.4 gives you a complete breakdown of how to perform the superposition calculations. In the theory overview, it states that the superposition theorem states that in a linear, bilateral, multi-source DC circuit, the current through or the voltage across any particular element may be determined by considering the contribution of each source independently, with the remaining sources replaced with their internal resistance. The contributions are then summed, paying attention to polarities to find the total value. It says superposition cannot in general be applied to nonlinear circuits or to nonlinear functions such as power. So under equipment, you can see we're going to be using the adjustable DC power supply. This is the Agilent model E3630A, and I'm not going to bother with its serial number. The digital multimeter is the Mastech MSM 9803, and I'm not going to bother with its serial number. I've measured my 4.7 k ohm resistor is 4.61 k ohms. My 6.8 k ohm resistor is 6.77 k ohms. My 10 k ohm resistor is 9.88 k ohms. My 22 k ohm resistor is 21.38 k ohms. And my 33 k ohm resistor is 32.52 k ohms. Our first schematic is figure 10.1, and you can see I've left you space to put your calculations. And today we're going to do a second circuit, figure 10.2, and once again I've left you space for your calculations. So under procedure, step number 1, we're going to start with voltage applications. So we're to consider the dual supply circuit of figure 10.1. We're using E1 is equal to 6 volts, E2 is equal to 10 volts, R1 is 4.7 K, R2 is 6.8 K, and R3 is 10 K. It says to find the voltage from node A to ground, superposition may be used. Each source is considered by itself. So this is figure 10.1. And I've filled in the 6 volt supply, the 10 volt supply, the 4.7 K, the 6.8 K, and the 10 K ohm resistors. So it says to first consider source E1 by assuming that E2 is replaced with its internal resistance, which is a short, as shown in figure 10.1a. In figure 10.1a, I've redrawn my schematic with E2 shorted out. So we're to determine the voltage at node A using standard series parallel techniques and record it in table 10.1. we're to make sure to indicate the polarity. So looking at figure 10.1a, you can see that E2 has been removed and replaced with a short. So to find the voltage at point A, we can use voltage divider law, but first we need to find the equivalent resistance of R2 in parallel with R3. So looking at the calculations with E2 shorted, we need to find out what R2 in parallel with R3 is. So we're going to use the product over the sum calculation. So we're going to take 6.8K times 10K divided by 6.8K plus 10K, and that works out to 4.048K ohms. Now to find the voltage at point A for circuit A, we're going to use voltage divider law. So we're going to take R2, R3 parallel, which is 4.048K, and divide it by the total resistance of the circuit, which is 4.048K, plus R1, which is 4.7K, multiply it by the source E1, which is 6 volts. So the voltage at A is going to be 2.776 volts, and please put in the plus sign. So in table 10.1, under VA theory, E1 only, I record plus 2.776 volts. Continuing on under procedure, step number 1, we're to repeat the process using E2 while shorting E1 as in figure 10.1b. Looking at figure 10.1b, this is with E1 shorted out. So I've redrawn the circuit. We need to find the voltage at point A, so we're going to use the voltage divider law. To use that, we need to find out what R1 in parallel with R3 is. So looking at our calculations with E1 shorted, we're going to find out what R1 in parallel with R3 is. So that's 4.7K R1 times 10K R3 divided by 4.7K plus 10K, and that works out to 3.197K ohms. So applying the voltage divider law, we can find the voltage at point A for circuit B as being 3.197K, which is R1 in parallel with R3, divided by 3.197K plus the 6.8K ohms of R2 times E2, which is 10 volts, and that works out to plus 3.198 volts. In table 10.1, under VA theory, for E2 only, I record plus 3.198 volts. Now finally, we're to sum these two voltages and record the results in table 10.1. So going back up to figure 10.1, where we have E1 is 6 volts and E2 is 10 volts, they're telling us that the voltage at point A is equal to the voltage at point A, circuit A with E2 shorted, plus the voltage at point A in B circuit with E1 shorted. So that works out to be plus 2.776 volts plus the positive 3.198 volts, and that works out to plus 5.974 volts. So in table 10.1, under VA theory, for E1 and E2 combined, I record plus 5.974 volts. Under procedure, step number 2, it says to verify the superposition theorem, the process may be implemented directly by measuring the contributions. We're to build the circuit of figure 10.1 with the values specified in step 1. However, replace E2 with a short as in figure 10.1a. Do not simply place a shorting wire across source E2. This will overload the power supply. So we're actually going to disconnect it to put a short in the circuit. Alright, so this is my circuit, and you can see I've tried to wire it up exactly like the schematic. So here I have R1, it's 4.7K. It makes contact in this bus line right here with R2, which is my 6.8K, and R3, which is my 10K. So you notice I have a red wire indicating power is coming into R1, and I have a red line on the other side indicating that power is coming into R2, and then I have a black lead at the bottom indicating this is my common from my power supply going to R3. So looking a little further back, you can see if I press the +6 on the meter, I have 6 volts coming in from the +6 terminal to this side of my circuit, so that is E1. If I press the +20 volt meter button in, I have 10 volts, and it's coming out of the +20 volt terminal to this side of my circuit, so it is E2, and the common is coming to the bottom of R3. So that's the circuit set up as it needs to be. Now what they're saying is we need to replace E2 with a short. So what we're going to do is we're going to disconnect E2. And then instead of going into the power supply at +20, we're going to go in to the common. So now we have shorted from here to the common. And you'll notice there's no yellow indicator lights on the power supply indicating there's an overload. A lot of times students will try and short from this point to this point and leave the power supply in. The yellow light comes on and eventually something gives way. So this is the safest way to replace E2 with a short. Under procedure, step number 3, we're to measure the voltage at node A and record it in table 10.1. Be sure to note the polarity. So the red lead from the voltmeter goes to the top of the 10K ohm resistor, which is R3. The black lead from the voltmeter goes to the bottom of the 10K ohm resistor. And my voltage reading is 2.803 volts. So in table 10.1, under VA experimental, for E1 only, I've recorded plus 2.803 volts. So under procedure, step number 4, we're to remove the shorting wire, and we're going to reinsert source E2. Now we're also going to replace source E1 with a short, as in figure 10.1b. And we're going to measure the voltage at node A. We're to record this in table 10.1 and be sure to note the polarity. So what we're going to do is take the red lead that is E2 and put it into the +20 volt terminal. And we're going to take the red lead that was the +6 volts and plug it into the common terminal. So now we're effectively shorting out E1. The red lead from the voltmeter is on the top of R3, which is the 10k ohm resistor, and the black lead from the voltmeter is on the bottom of the 10k ohm resistor. My voltage reading is 3.154 volts. If it was negative, there would be a negative sign showing up here, but this is positive 3.154 volts. So in table 10.1, under VA experimental, for E2 only, I've recorded plus 3.154 volts. Under procedure, step number 5, we're going to remove the shorting wire and reinsert source E1. Both sources should now be in the circuit as in figure 10.1. We're to measure the voltage at node A and record in table 10.1. Be sure to note the polarity. Determine and record the deviations between theory and experimental results. So what we're going to do is we're going to remove the wire that went to E1 that we placed into common, and we're going to put it back into the plus 6 volt terminal. So now we have the plus 6 volt terminal supplying E1, the plus 20 volt terminal supplying E2. So we now have both sources in our circuit. The red lead from my voltmeter is still on the top of my 10k ohm resistor, which is R3. The black lead from the voltmeter is still on the bottom of the 10k ohm resistor. The voltmeter is reading 5.87 volts. So in table 10.1, under VA experimental, for E1 and E2, I've recorded plus 5.87 volts. I'm going to leave you to calculate the percent deviation. Moving on to procedure step number 6, you can see we're now going into current and power applications of superposition theorem. And just to give us a head start, under figure 10.2, I've given you a simulation showing you what the answer should be when we've done our calculations. So under procedure, step number 6, we're to consider the dual supply circuit of figure 10.2 using E1 equal to 6 volts, E2 equal to 10 volts, R1 is equal to 4.7K, R2 is equal to 6.8K, R3 is equal to 10K, R4 is equal to 22K, and R5 is equal to 33K. It says to find the current through R4 flowing from node A to B, superposition may be used. Each source is again treated independently, with the remaining sources replaced with their internal resistances. It says to calculate the current through R4 first, considering E1, and then considering E2. Then sum these results and record the three values in table 10.2. So we want to measure the current flowing from point A to point B. So point A is going to be the positive side of our ammeter. Point B is going to be the negative side of our ammeter. So when just the 6 volt supply is connected, current will flow normally, as we expect. With E1 shorted out and only E2, current will be flowing back the opposite direction. So we have to remember that these currents will be negative. So looking at figure 10.2, I've filled in the plus 6 volt supply, the plus 10 volt supply. R1 is 4.7K, R2 is 6.8K, R3 is 10K, R4 is 22K, and R5 is 33K. And we want to find the current flowing from point A to point B. So A is the positive side, B is the negative side. So looking at figure 10.2a with E2 shorted, and you can see I've redrawn the schematic diagram with E2 shorted out. Now we need to find the current flowing from point A to point B. To do this, we're going to use the current divider law. So we need to start by finding the total current flowing through the circuit, which is also the total current flowing through R1. At which point we can use the current divider law to find the current flowing through R4. So to start with, we need to find out what R2 and R5 in parallel is, add in R4, and then find out what that is in parallel with R3. Then add R1 to come up with our total resistance of the circuit. So taking a look at the calculations with E2 shorted, I've decided to calculate what R4 plus R2 in parallel with R5 is going to be. So that's going to be equal to 22K plus the 6.8K times 33K divided by 6.8K plus 33K, and that works out to 27.638K ohms. Now to find RT, I'm going to take R1 and add R3 in parallel with the R4 plus R2 in parallel with R5 that we just calculated. So the equation becomes 4.7K plus 10K times 27.68K divided by 10K plus 27.638K. And that works out to 12.043K ohms. So that's the total resistance of our circuit. I now need to find out what the total current flowing through the circuit is, and the total current flowing through the circuit is the same current flowing through I1. So IT is equal to ET over RT. So our applied voltage is 6 volts, and we just calculated our total resistance to be 12.043K ohms. So this works out to be a total current of 498.215 microamps. And keep in mind that that is positive. The next step is to find the current flowing through I4. So remember, to use the current divider law, what we need is the input current, which is I1 or IT, and we take the resistor we don't want, which is R3 or 10K ohms, divided by the total resistance, which is R3 plus all of this part of the circuit. So we've calculated this earlier as being R4 plus R2 in parallel with R5. So to calculate I4, we're going to take R3 divided by R3 plus the R4 plus R2 in parallel with R5 that we calculated earlier as 27.638K ohms times the applied current, or I1. So that's equal to 10K divided by 10K plus 27.638K ohms times the 498.215 microamps. And that works out to be equal to plus 132.37 microamps. So in table 10.2, under I, R4 theory, for E1 only, I've recorded plus 132.37 microamps. Now I want you to notice that in figure 10.2a with E2 shorted, the current does indeed flow from point A to point B. So the current that we calculated through I4 is indeed positive. So when we look at figure 10.2b with E1 shorted, you can see I've redrawn the schematic and E1 is indeed shorted out. Now we still want to find out what the current flowing from point A to point B is going to be, but because we have a 10 volt supply, the current's actually going to be flowing backwards against our sensing resistor that we started with. So when we go and do our calculation, we're going to have to remember either this is going to be a negative current, or when we do our final calculation and add the two together, we're going to have to subtract this current because it's flowing in the opposite direction. Now to solve this particular circuit, what we need to do is find out what the total resistance is so we can find the total current, and then use the current divider rule to find out what the current flowing through R4 is going to be. So the total resistance is going to be R1 in parallel with R3 plus R4 all in parallel with R5 plus R2. So once again, I've broken it down into steps so that we can find out what this resistance is going to be, because we're going to use it later in our calculations. So looking at our calculations with E1 shorted, the first thing I'm going to do is find out what R4 plus R1 in parallel with R3 is equal to, and that equals 25.197 k ohms. The next step is to find RT, and that's going to be equal to R2 plus R5 in parallel with R4 plus R1 in parallel with R3, which we just calculated above as 25.197 k ohms. So this works out to be 6.8k plus 33k times 25.197k divided by 33k plus 25.197k. So RT works out to be 21.088 k ohms. My next step is to find the total current, IT, which is also the current flowing through resistor 2, so that is I2. So this is going to be equal to ET divided by RT. So our applied voltage is 10 volts divided by our total resistance of 21.088 k ohms. And that's equal to 474.203 microamps. Now to find I4, I'm going to use the current divider rule. So to use the current divider law, what we need to do is take the current flowing through R2, which is IT, and then the current divider law says you take the resistance that you don't want the current flowing through, so that's R5, over the total of R5 plus the rest of the resistance in the circuit. In this case, it's R4 plus R1 in parallel with R3 that we calculated earlier.
So using the current divider rule to find I4, I take R5, divide it by R5 plus R4 plus R1 in parallel with R3 times the total current IT. So that's equal to 33K divided by 33K plus 25.197K times 474.203 microamps. And that works out to 268.892 microamps. Now keep in mind, this is flowing in the opposite direction to which we want. We want the current flowing from point A to point B, and the plus 268 is the current flowing from point B to point A, so we have to record this as minus 268.892 microamps.
So in table 10.2, for R4 theory, E2 only, I've recorded minus 268.892 microamps. Remember, the sensing arrow is in opposite direction to the flow of the current that we just calculated. So under procedure, step number 6, to finish off, we have to sum these results and record the three values in table 10.2. So to finish off, under figure 10.2, where we have E1 at 6 volts and E2 at 10 volts, so under total calculations, I4 is going to be equal to I4A, that's where E2 was shorted out, plus I4B, that's where E1 was shorted out. So in this case, it's going to be equal to a positive 132.37 microamps plus the negative 268.892 microamps, and that's going to work out to be minus 136.522 microamps. So when you look back at figure 10.2 simulation, you can see Multisim has given us a reading of minus 0.137 milliamps, so that's 137 microamps, and it's negative. So we wanted to sense the current flowing from point A to point B, and in reality, because of the 10 volt supply on this side, the current is actually flowing backwards, and that's why we're getting a negative reading. So under table 10.2 for R4 theory, with E1 and E2 in the circuit, I've recorded minus 136.522 microamps. So under procedure, step number 7, we're to assemble the circuit of figure 10.2 using the values specified. So this is my circuit set up on the trainer, and you can see I've set it up exactly like the schematic. You can see this is R1, so this is source E1 coming in to R1, which is my 4.7 k ohm resistor, with my 6.8 k ohm resistor that comes out to supply E2. Then you can see at the junction of R4 and R2 is R5, which is my 33 k ohm resistor that goes to ground. At the junction of R4 and R1, I have R3, which is the 10 k ohm resistor that goes to ground. And don't forget this little jumper here so that both resistors get ground or common from the supply. So you can see out of my 6 volt terminal, I have 6 volts going to my circuit, so that's E1. Out of the 20 volt terminal, I have 10 volts going to my circuit, and that is E2. We're going to replace the source E2 with a short and measure the current through R4. Be sure to note the direction of flow and record the results in table 10.2. Now it says in the lab to replace source E2 with a short. So we're going to disconnect the red lead from the power supply and put it into the common terminal. So now I've replaced E2 with a short. Now to measure the current through R4, I've disconnected R4 from the bus line, and I've connected the positive of the ammeter to the leg of R4 that I just pulled out of the circuit. The common of the ammeter I've hooked up to one of the two resistors that are still in the bus. Now remember, from step 6, we want to find the current flow through R4 flowing from node A, so this is node A, to node B, and this is node B. So we're sensing the current flowing this way, so that means that this is the positive side, this is the negative side. So my reading for E1 only, that's with E2 shorted to common, I'm getting 135 microamps. Notice it's 0.135 milliamps. Proper engineering notation says we should record this as 135 microamps. So in table 10.2, for I, R4 experimental, with E1 only, I've recorded plus 135 microamps. Under procedure, step number 8, we're to replace the short with source E2 and swap source E1 with a short. We're to measure the current through R4, be sure to note the direction of flow, and record the result in table 10.2. So I'm not going to remove my ammeter, I'm just going to leave it there. I'm going to take the red lead out of the common of the power supply and put it into the plus 20. And then E1 is going to be replaced with a short. So I take E1 out of the power supply and put that into the common of the power supply. So that's now given me a short between E1 and common. Notice the yellow overload indicators are not on because we took the lead out of the plus 6 and put it into the common. So this is my reading for E2 only. That's with E1 shorted. I'm reading minus 274 microamps. So in table 10.2, for I, R4 experimental, E2 only, I've recorded minus 274 microamps. Under procedure, step number 9, we're to remove the shorting wire and reinsert source E1. Both sources should now be in the circuit. We're to measure the current through R4 and record in table 10.2. It says be sure to note the direction, determine and record the deviations between theory and experimental results. So I'm still leaving my ammeter where it was. This is E2. This is E1 that was shorted, so I'm going to disconnect the red lead from the common and put it back into the plus 6 volt terminal. Now I have both sources connected to my circuit. With E1 and E2 connected to the circuit, I'm reading minus 139 microamps. So in table 10.2, under I, R4 experimental, For E1 and E2, I've recorded minus 139 microamps. I'm going to leave you to calculate the percent deviation. Under procedure, step number 10, it says power is not a linear function as it is proportional to the square of either voltage or current. Consequently, superposition should not yield an accurate result when applied directly to power. Based on the measured currents in table 10.2, calculate the power in R4 using E1 only and E2 only, and record the values in table 10.3. It says adding these two powers yields the power as predicted by superposition. Determine this value and record it in table 10.3. So looking at table 10.3, we need to calculate the power for R4. So I need you to remember that V equals IR and power equals V times I. So substituting the V from above into our power formula, we get power equals IR times I. So power is equal to I squared R. So for E1 only, we take 135 microamps squared times 22 k ohms, and that's equal to 401 microwatts. For E2 only, we take minus 274 microamps squared times the 22 k ohm resistor, and that works out to 1.65 milliwatts. Then when we add these two together, we come up with E1 plus E2 as being plus 2.05 milliwatts. Continuing on under procedure, step number 10, it says the true power in R4 may be determined from the total measured current flowing through it, using the experimental current measured when both E1 and E2 were active from table 10.2. We're to determine the power in R4 and record it in table 10.3. So in table 10.3, for E1 and E2, we measured minus 139 microamps. So we take the minus 139 microamps, square it, times the 22 k ohms of the resistance, and that works out to 425 microwatts. And you can see that's totally different from adding the two that we got previously using superposition theorem. On the last page of the lab, we have 4 questions for you to answer based on your calculations, observations, and conclusions. When you've completed your lab, leave your circuit set up on your trainer so your instructor can verify that it is operating correctly, and they will initial your lab to indicate that it is complete.